Hey everybody, I'm Matt. I'm with Binary Builders, so we are core maintainers of the Cosmos SDK. So my day-to-day is doing that, and one of the things I got to work on that I was most excited about in 2023 was improving IAVL v2. Received a lot of complaints about performance with IAVL, yeah, so that spawned some working groups, and one of the results of that was an opportunity for me to take a really deep dive into IAVL, the commitment structure, and IAVL, the library, and learned a lot of really cool things along the way. So this is really a discussion about what I discovered and a report of the results. So here we go. So first, I'm just going to, really quick, from 100 feet, this is what IAVL is to me and to a SDK developer. The first thing is IAVL as a commitment structure. So it is a immutable merkelized AVL tree, which is a self-balancing BST, binary search tree. So this is the form that the commitment structure takes. Some interesting properties of an AVL tree that made present some challenges to performance that probably a lot of people here know about is that since an AVL tree is self-balancing, or insertion order matters. So we can't change the order in which, you can't necessarily change the order in which you do sets and deletes. So that's what this is telling us. They're not always equivalent. That produces some unique challenges for concurrency and other things. This is just an illustration of that happening. I think it's really cool. Really smart people, invented this a long time ago. So, in the 70s, don't applaud me. Applaud AVL. So another very unique property of the IAVL tree is the way that classically in an AVL tree, inner nodes will carry a value. In our AVL tree, only leaf nodes carry values. So actually each logical key appears twice in the tree. So some opportunities to correct that maybe. So that's AVL, the commitment structure, and then AVL, the library, is built on top of that. It does a lot of things for you. It's a batteries included library. Handles things like caching, encoding of nodes, hashing, pruning, that is to say, of course, state grows indefinitely unless you delete old state. That's what pruning is. Snapshot import, snapshot export, get, set, delete, and iterate. Iterate is really fun to need to support, but we do. And something really fun in there too, I think Osmosis team may have even worked on this, is the fast node storage system, which I won't get into here, which was essentially just a way to speed up iteration because things were so slow. And it has gone through 3 major versions, V0, V1, and V2. I'm going to talk a little bit about the changes in V1, but I'm going to focus mostly on the changes in V2. Okay, so that's out of the way. I'm going to start kind of at the end with the data, with benchmarks. That's where I would want to start if I were sitting there. So, I'm not just shilling something. We're going to talk about data, which is my favorite thing. I'm very passionate about storage. I think it's really fun to solve problems where you're up against the laws of physics and really thinking about how can you make this thing go as fast as possible. So that's what this is. So here we go. A little bit first about the data set. I wrote a tool to generate data. You can investigate that if you want for these benchmarks. I would be remiss if I didn't mention it because a benchmark is only as good as the data set used to produce it, I think. So it's a generated data set, but it was based on some research I did about an Osmosis snapshot. So version 1 is 46 million key values across 17 trees, 10 gigabytes of data, and then each version includes a change set comprising 8 million more sets than 1.5 million more deletes, 4 gigs, and the platform was tested on my laptop, although I did also do this on other machines with similar results, but the benchmarks here are from my M2 MacBook. Okay, so first one, kind of boring. This is just the time it takes to build version 1. Not much to say about it, although you can see V2 is already pulling away. So quite a bit faster. 9 minutes to ingest those 40 million gets and sets, or just sets. And then V1 is faster than V0. So faster is better, right? I think so. Okay, this is my favorite slide. So we'll just take this in for a minute. I think it shows a pretty impressive iterative performance improvement. Yeah, so V0, not quite 10x of V1, but certainly this is my favorite implementation of V2 down here. This is actually 10 times faster than V1. So I worked really hard to try to get the numbers there, and there's a lot of tweaks and configurations you can make to V2 as it is today. And that's what kind of all these different configuration sets are. Some of them came out of development, and I just kind of kept those configurations around. They're still in the code base today. Okay, so checkpoint doesn't mean anything to you right now. It will later. There's a slide on what checkpoints are, but essentially what V2 is doing is it's writing internodes to disk at intervals. So these tests were taken checkpointing every 50 blocks, 50 versions. This async commit is just saying we're committing to disk optimistically, and then we're bailing out if the commit fails. In other words, you can write the tree to disk and still proceed with work while that's happening. So just leveraging concurrency. So predictably, async commit is a little bit faster than a synchronous commit. These two down here, hot start means that a portion or all of the tree was loaded into memory at startup. In a real world situation, that could happen gradually over time, but sort of pre-warming the cache is what that means. We pre-warm the cache. And V2 archive is kind of is it really an apples to apples comparison of what V1 and V0 are doing, which is they don't checkpoint. They save every version to disk. I know this is super technical, and if you don't have the context for IAVL, this might not make any sense, but that's what this talk is. So bear with me. Well, it'll hopefully make a little bit more sense later. But so this is my favorite slide, and this is my favorite configuration: is hot evict only leaves. This is where I got the 10x performance boost on V1 from, which is to say, essentially the whole tree is kept in memory except for the leaves, which for a binary tree is half the tree. So you can evict half your tree and save that memory, and you're going to disk just for leaves. You're not going to disk for inner nodes. So pretty cool. Oh, and ops per second are either a set or a delete. So one set or one delete. That's the metric. Okay, here's another analysis, memory usage, which is important. Of course, if you put the entire tree into memory, that's the fastest things can go. Oh, I think I forgot to mention that. That's what this is. This is, I guess you could say, the theoretical limit today of IAVL, 70,000 ops per second. That's with the entire tree in memory. So just traversing an in-memory AVL tree. So that uses the most memory, 28 gigs, and then you can kind of see the distribution here. Yeah, I will totally get there. There's a data point that's going to pop up in just a second. So V1 key format is slightly bigger than the V0 key format in one of the next slides. So that explains the increased memory usage. High and low has to do with checkpointing. So during checkpoints, basically a write buffer is filling up and then empties out. So during a checkpoint, memory is going to go up, and then it'll come back down to the 8 gig operating level with this benchmark. What else to say here? Hot start loads the entire tree in memory. I said that. Yeah, I tested this version of IAVL v2 on Osmosis mainnet, and that was tested with the synchronous commit profile. There's a slide for that next. Here we go. Okay, so I did test this. I forked an Osmosis, the Osmosis SDK and Osmosis sometime last year, and I ran this test on mainnet. There's a really in-depth discussion. I'm not going to get into it here, but basically this is what we observed in a real world live chain situation for performance improvements. Definitely a really big gap between benchmarks and what we saw on chain, but we did see mean commit time 10 times faster, mean get time 5 times faster, overall block throughput increased by 2.5x, and epoch time was roughly halved. So that was great to see. This discussion also generated quite a bit of research for me and maybe the Osmosis team, I don't know. I produced some flame graphs to see just if I could narrow down why the performance improvements to the state layer weren't flowing all the way up to block throughput. So that's definitely an area for more research. Okay, so key takeaways from the benchmarks. Yeah, I already said that. Ops per second are gets and deletes. They're also a good proxy for reads because as you're traversing a tree, you need to read inner nodes from disk. So even though the gets and sets are write operations, they're also exercising how quickly you can read from disk. Talked about that. Yeah, and there's been progressive speed improvements, so we're going in the right direction. Yeah, and so there are a lot of kind of features in a configurable API in V2. I can't really recommend which configuration is best because it depends on the operator. If you're willing to trade memory, you can go as fast as possible. And if you want to save memory or have other considerations, you can tweak things to how you want. Okay, so what changed? Why is everything so much faster? This is embarrassingly simple. I think you would have all come to the same kind of conclusions if you had been as deep into the code as I was. And yeah, I'm just kind of sharing it with you and looking for feedback on how we can keep iterating. So the first thing that was a big change from V0 to V1 was the key format. There was a working group, I guess maybe a year and a half ago now, where this was floated and seemed like a good idea. I don't even think we tested it at scale before implementing it. I think my tests were some of the first ones to really prove it out, but it turned out to be true. Here we go. So the V1 way of hashing a node and storing it on disk, which is to say actually in the database, not in the tree where it's stored on disk, was to produce a hash of the node. Of course, hashes are a uniformly random distribution, so there's no data locality between nodes at all. So you're not really leveraging any kind of caching. So that was the thesis. So V1 instead keys nodes by a synthetic key, a concatenation of the block height version, and a sequence number, which is essentially just the order in which the write arrived at the library. And V2, so a high likelihood of data locality and traversal, as you'll see in the next slide. And V2 maintains this same key format because it works really well with B trees, which IAVL v2 is implemented today with a B tree, but I'd like to do it with LSM also just to see the difference. A neat thing about this with B trees is B trees kind of are awful for random writes, but when you're using them this way, you're actually appending to the end of the B tree, so you don't need to update, you don't need to do as much rebalancing of the index. You're kind of just appending to the end of it, which is way, 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 way faster. So here we go. This is why the V1 node key format is better. If you can imagine, this is like this is a node. This is a leaf node that just got updated. So all of its parents have the same version. That's what this red line is. It's the traversal path. So now when I go to traverse this path on disk, there's a very high likelihood that maybe even those nodes are sitting in the same page. Maybe they're even sitting in the same page, right? If a page is 4 KB and our nodes are 800 bytes, you know, they could all be sitting in hot cache. And then all those properties kind of flow all the way up through the system in memory, in your DB implementation. So those are really, really great properties that we want to keep. So that's why V2 keeps that same node key format. One thing here that confused me for a long time, a little bit was, and it is a little bit confusing, is that this is not the same thing as your application key. So if you're keying something on, a count, this is a different key. This is the key that represents where the node is actually stored on disk. Okay, so let's talk about the commit procedure, the secret sauce, very obvious secret sauce in V2. Why is it faster? Well, it's just doing less work. It's just doing less work. We're not flushing branch nodes, inner nodes to disk on every commit. We're sort of just deferring that and doing it periodically. So in one sentence, that's kind of why things are faster. Kind of surprised it wasn't happening already, but that's what V2 does. So on each commit, what IAVL V2 does is it hashes the tree, writes the root node, so the root hash. Then it only writes the leaf nodes and then leaf deletes, and it does this in order so that you can replay the tree to a given state given the log. So it's a write-ahead log. It's a wall. Technically you could also just replay transactions, but of course this is a lot faster because you don't need to execute a transaction in the state machine. You just replay the changes that resulted. So the next step in the commit procedure is to determine if the tree could checkpoint. There are a few conditions today that could trigger a checkpoint. One, I don't enumerate them here, but maybe I'll just tell you. One is just a mod, just mod 50. So if I'm at just write every 50 blocks or whatever it is. Another condition that could trigger a checkpoint is memory usage. So if memory usage is getting high, we flush the disk and then evict a portion of it. And when the tree is checkpointing version N and the last checkpoint was version M, only nodes with version M greater than M are present in the version checkpoint. So just essentially what you're writing to disk is a diff. It's a diff of all the work that's happened since the last time you checkpointed. So all those other intermediate nodes and all the intermediate versions just don't make it to disk. So we're not doing as much I/O and things are faster. So that shouldn't be surprising. It wasn't to me, but I'm still delighted by the results. Okay, so here's just a kind of a pictograph of a checkpoint. The red nodes are checkpoint events, and the gray nodes are events where we didn't checkpoint. So we only wrote the root hash and the leaves to disk. So if I wanted to replay to some block, so say I want to replay to this block here, I'm just going to load the full checkpoint, kind of like a keyframe. If you know anything about video encoding, works kind of the same way. I'm going to find the previous full snapshot, kind of. It's not really a snapshot, but I can load it from disk that way, and then just replay my wall. So I feel like I've talked that to death now. Hopefully you kind of get it. So here's just a illustration of that same thing. An interaction between the tree and the writer. In IAVL v2, the writer is actually a separate thread. So we can checkpoint when n blocks have elapsed, when working memory is approaching a ceiling, and on checkpoint we accumulate dirty leaves and branches. If configured, evict leaves to save memory. If configured, evict branches below depth H. I love this feature. It took, it's one of the last things I implemented as a memory saving device. So yeah, just evicting nodes that are below, say, height 16 can save you memory. So pretty cool. And optimistic commit, which is shown here. Just showing that this happens in the background. So just a normal operation, right? Commit. Yes, I've committed. Thank you. Please commit more leaves, but also checkpoint. I'm going to tell you I committed the leaves right away. Please commit more leaves. Oh, and by the way, that checkpoint's done, and the leaves are done too. So it's an asynchronous process. So taking advantage of write gaps to do that. Okay, so the caching strategy. I was very confused about the layers of caching in the SDK, and still am, and also present in IAVL when I started looking at it. So I asked myself, do we even need a cache? And I couldn't convince myself that we did. IAVL v0 has an LRU cache to kind of put thing. It's very strange. Nodes get evicted out of the tree and then immediately pulled back in, which makes sense in some contexts, but it didn't really make sense to me to do it here. So I just threw out the cache and decided, why don't we just let the tree be the cache, which seems to have worked okay so far. Right, just talked about that. And instead, create an eviction policy that is either based on layers from the bottom or depth from the top. So if you evict a leaf, you're evicting something with height 0, and if you're evicting inner nodes below, height 16, then you're kind of calculating what to evict as you recurse down the tree. Yeah, and evicting leaves is half the memory of your tree, so a big savings for just a little bit of I/O. Talked about that. Okay, so the disk layout for V2 is also a little bit different. I made some decisions about how to separate things. In the current implementation, everything goes into the same, oh wow, red flag already. It's the same database. I could talk about this all day. We'll skip that. Pruning's not so important. You all know what pruning is. Okay. B-tree versus LSM. This is very interesting. I want to get to it. IAVL v2 does use a SQLite as a backend, which implements a B+ tree. LSMs are optimized for write. B-trees are optimized for read. SQLite profiled faster than Go level to be on random reads. And IAVL workloads are actually read heavy. And I got it to the point where bulk sequential writes in SQLite wall mode are actually profiled for me faster than level DB, so that's why I went with it. I'd still like to try a different implementation to prove that out, though. Yep. Okay, so next steps. I would like to implement and profile an LSM tree. I like to do more mainnet integrations to close the gap between the bench and production tests. I like to do mainnet tests with async commit, particularly for the epoch blocks. I didn't get a chance to test that. It was implemented after. Okay, and this is what I think I would like to do next. A little bit hard to explain because it's still in the ideation phase. There's a paper from 2002 that sort of describes a way to lay out nodes in memory that I think would be the optimal way. But the thing to understand is that we have an AVL tree, and there's also a tree on disk. The database that's storing the tree is also a tree. So you're storing a tree within a tree. The problem is we want to close that gap. We want our tree layout to be as close as possible to the disk layout. So how can we do that? One idea is to use this from this paper, the VEB layout, which I forget who wrote. There's a post from a few months ago. I forget who it was who described doing something like this for Ethereum. This is the order that we want to use, and I will show you here. Probably not easy to see, but essentially what this is doing is it's optimized to for data locality in subtrees. So maybe each of those blocks is a page on disk, and and all of the nodes can fit into. So maybe if we traverse from top to bottom, we only have to do like 3 fetches from disk or something. This is what makes B-tree implementation so fast. Database researchers figured this out years ago. That's why basically every major RDBMS is based on a B-tree. So why not do the same thing? Okay, so thank you very much for your attention. I am Matt, and if you have any questions, let me know. Talk now or later.
Okay, yeah. You kind of like went over the pruning section really quickly. But actually, I'm very interested in this. Like, is there any difference between IAVL v2 pruning and IAVL v1 and so what is it?
Async, yeah. It does it asynchronously. No. I think there's a PR open for V1 that to do something like that, which is my colleague John opened up after I published this. Oh, cool. How's it going? Yeah. I kind of I pioneered that idea, and then it was a good one. So it's I think we're trying to backport something like it to V1 too. Yeah. Yep. You're welcome.
So there are async commit, sync commit, and also archive modes. that don't really check the whole tree into the memory. And so from a high level, they don't trade memory for better performance, but they still have different performance characteristics. What are the pros and cons of each of them? How do people choose basically between them?
Sorry if I skimmed over that too quickly. The only mode that actually stores the whole tree in memory was the 70K ops a second mode. The rest of them actually don't store the whole tree in memory. That was sort of just for me to show, like, to prove to myself what's the fastest we could possibly go. I don't know if that answers your question.
So what would you recommend for like
Yeah, I mean, if you have the memory, I would say just evict leaves, because for a tree of size 40 million, that was 14 gigabytes, which is about as much memory as V1 and V0 are using. So, and that the caveat there, of course, is that you can't do historical proofs against every version for the last, forever, because you don't have them on disk. But if you have a node that needs to provide that, then you'd have to use archive mode.